Hello students, the 11th standard. We are going to start a topic that is the types of semiconductor. Students, it is only a theoretical part. Okay. This semiconductor are of two types. First is the intrinsic semiconductor and second is the extrinsic semiconductor. Okay. First is the intrinsic semiconductor and second is the extrinsic semiconductor. In intrinsic semiconductor, these are the pure semiconductor when the germanium or a silicon atom get combines to form a solid. They arrange themselves in the orderly pattern called as a crystal. It is a definition for the crystal. You have to keep this definition in your mind. When germanium or a silicon atom combines to form a solid, they arrange themselves in an orderly pattern called as a crystal. The germanium and the silicons are tetravalent, that is, there are the 4 valence electrons. As discussed previously in a previous topic, the outermost orbit, whatever the outermost orbit which is occupied or which is covered, gives you the electrons. So at this, the 4 valence electrons have been used. For a stable atom, the 8 valence electrons are necessary. By sharing the 1 electrons each with a neighbor with the 4 atoms, the central atom gets 8 electrons in its valence orbit. Therefore, it becomes a stable. Okay. Since when we are using this particular formation, the forces that holds the atom together is nothing but it is a covalent bond. When such type of the pure impurity of a silicon or a germanium is called as a intrinsic semiconductor. The pure form, this it is important. Pure form of germanium or a silicon is called as an intrinsic semiconductor. It is a one simple definition. Okay. Then if the temperature is increases beyond the degree Kelvin, 0 degree Kelvin. What is the temperature? That is a 0 degree temperature. The heat energy band breaks through the covalent bond. Here you will be observing the diagram. This is the diagram which is the structure. It is a crystalline structure for the silicon. It is a silicon. Here the silicon has been used. The outermost orbit, the 4 valence electron is there. Here this is the structure which you have drawn. What the dotted part which is drawn inside, it is nothing but it is called as a valence electron, and this holds the part, this silicon, whatever it is get combined. This combined part is nothing but it is a covalent bond. Okay, so it is the crystalline structure, or you may say the structure for the silicon or the intrinsic semiconductor. Okay, so here you will be observing the parts of this. When the 0 degree Kelvin, the heat energy breaks the covalent bond. Means that covalent bond, this covalent bond is going to be break, and as soon as the covalent bond gets break, the valence electrons which is present inside the covalent bond will get combined with the another, and that formation, the valence electrons goes from valence band to the conduction band. As last class, the valence band and the lastly the conduction band was there. When at a certain temperature it gets break, the electrons will be get formed and the break from the valence to the conduction band, and it is occurred. The energy required for that purpose is equal to the forbidden energy gap. That is forbidden energy gap. It is represented by the Eg. It is represented by Eg. The value for the energy gap in this, it is a 1.12 electron volt. Okay, for silicon, and for germanium it is 0.72 electron volt. So you have to mark this one. The value for the energy gap, it is 1.12 electron volt, and for the silicon it is 0.72 electron volt for the germanium. Okay. When an electron goes from the valence band to the conduction band, the hole is created in the valence band. Okay students, it is very much clear to you. When you are using this formation, when this type here, when this part if you are able to observe this one, this part, the valence electron, okay, this valence electron, if it gets break, covalent bond get break, what will happen? This valence electron tries to goes from this place to this place, means ultimately the hole will be get created like this, okay, and this valence electron tries to break this covalent bond, again the hole will be get created, again it tries to break the covalent bond, as it moves randomly from one to the another, the different covalent bond will get break and the number of the holes will be get occurred, okay. When at the same such an intrinsic semiconductor, the conduction is provided by the free electrons in the conduction band and by the holes in the valence band. When the formation is occurred, the formation will be look like this. It is the structure which is being used. Now here the energy band diagram we will be observing. Here in this energy band diagram, you have the first band, you have the second band, and the third band, as previously I told you, it is the valence band, and the last, in the fourth number, it is the conduction band. When the crystalline structure, you observe the crystalline structure, when the electron moves from one place to the another place, ultimately the covalent bond will get break, and due to that break, the holes will be get occurred in the valence band, and due to that, the conduction will be get occurred, and this electron will move to the conduction band. Whatever the electrons present here, it will get moved to the conduction band, and conduction band occurs the electrons, and in the valence band, the hole will be get created like this. As much of the electrons will try to move from one place to the another place, that much of the electron will be get occupied in the covalent bond, and in the valence band, that much of the holes will be get created. Okay, in the first and the second band, it will be same as remain as the same part. Okay, the next thing, it is a extrinsic semiconductor. This extrinsic semiconductor is nothing but in an intrinsic semiconductor there aren't enough free electrons and the holes produces a sufficient current. Due to the holes, it produces sufficient current. The process of adding the impurity, if you are adding the extra impurity, then to the crystal, it increases either the number of the free electrons or holes, is called doping. What is doping? If you are adding the extra impurity, okay, this one, the process of adding the impurity atom to the crystal to increase either the number of free electrons or hole is called as a doping. So only the one statement you have to keep in your mind for doping, the process of adding the impurity to the atom. Okay, this much word is meaningful. Okay, whenever anyone asks you what is doping, your answer will be the process of adding the impurity. And what will be saying? Only it is called as a doping. But if in a brief you have to say, then what you have to spell? Process of adding the impurity, the atom to the crystal increases either the number of free electrons or holes is called as a doping. The number of holes and electrons will be get added, or it increases, and due to that the doping is occurred. When the crystal of the intrinsic semiconductor has been doped, it is called as an extrinsic semiconductor. Okay. When the crystal of an extrinsic semiconductor has been doped, it is called as an extrinsic semiconductor. Now there are two types of the extrinsic semiconductor. First is the p-type and second is the n-type. First is the p-type and second is the n-type. The p-type semiconductor and the n-type semiconductor you have to study in the extrinsic semiconductor. So there are the 4 valence electrons in the germanium or silicon in the outermost orbit. Therefore they are tetravalent. Okay, tetravalent impurity. The impurity of the trivalent material can be added to the pure semiconductor. This is the doping process. Such doping conductor is called as a p-type semiconductor. Example they have given, that is a boron, aluminium, indium are the trivalent material. Only one or the two impurity atoms are added for a 10 to the power 6, the silicon or a germanium. Okay, this is the structure related to the p-type semiconductor. Suppose you have added the impurity that is aluminum. The outermost orbit for the aluminum is a 3, means one part is remaining. Means that particular one part is nothing but your the 4 valence electron, but here there is a 3, so one remains. This one is nothing but it is called as a hole, and rest of all the valence electrons is present. Again this aluminum it is get bonded with the silicon. The different formation has been seen here. So the covalent bond, it is being get connected with this one, it is being get connected with this one. Whole the system for this p-type semiconductor or also the n-type semiconductor, if you are adding that particular impurity, then only the name will be get changed in the middle, that is a AI, or the rest, that is a pentavalent or the next impurity. In a trivalent material, the 3 electrons are present in the outer orbit. They forms a 3 covalent bond. Okay, as discussed here, the aluminum, the 3 covalent bond will be get formed, and the one remains. The absence of the electrons in the 4th band is called as a hole. Means here, as I told you, one electron is absent. Here, the one electron is absent, and that's why the hole is get created. Okay, by controlling the amount of the adding impurity, the number of holes are controlled. Okay, the amount, what, by controlling the amount of the impurity added, the number of holes can be controlled. The conductivity of the p-type semiconductor is mainly due to the holes. Okay, with the increase in the temperature, some electrons and hole pairs are get generated. In a p-type semiconductor, the holes are the majority charge carrier. Here, this is very much important. Holes are the majority charge carrier and the free electrons are minority charge carrier. This statement you have to keep in your mind in this topic. Okay. Each hole may accept the electrons during the recombination. Since the trivalent impurity atoms are called as acceptor atoms. Okay. Trivalent impurity is nothing but it is a acceptor atoms. Clear to you? Then comes a n-type semiconductor. This n-type semiconductor, we have added the arsenic. As it is the arsenic. Okay. Now here the 4 instead of 4 there are the 5 electrons. Outermost orbit there is a 5 electrons. Means 1 electrons is extra. This 1 electron tries to go here and there. Ultimately, when it touches to this particular covalent bond, this will break this covalent bond and tries to attach with these electrons. Due to that, the maximum number of the electrons will be get occurred here, and the less number of the holes are present. If the impurity of the pentavalent impurity are added to the pure semiconductor, it becomes an n-type semiconductor. Which are the impurity? The arsenic, antimony, phosphorus are all the pentavalent impurity. When the 5 electrons are present in the outermost orbit, here the 5 electrons are present in the outermost orbit, this forms a free electrons. 1 electron is free. Okay, and due to that, the large number of electrons produces by the doping. There are the few holes. Have you observed the hole there? There are no holes. Only a few holes will be created by thermal energy. As the temperature increases, the electrons hole pairs are get generated. In the n-type semiconductor, the free electrons and the majority charge carriers and the holes are the minority charge carriers. The pentavalent atoms are called as a donor atom. That was the acceptor, but here it is a donor because it donates, because they produces a conduction band free electrons. It is get donated, and that's why it is the donor atom. Okay students, in the next class we will see the concept for the holes and the hole current. Okay.